Welcome. Hello, everyone. Welcome to Science Unwrapped. We're kicking off our spring series tonight, which is celebrating graduate student research. I'm Professor Brynja Kohler, and I'm Associate Dean and also Chair of the Science Unwrapped Committee. We have a couple other Science Unwrapped Committee members here, Neem Nguyen, Maria Rodriguez, and we are also happy to see Dean Ward, our Dean of the College of Arts and Sciences. On behalf of our college, we're excited to have all of you here this evening. A graduate student, for those of you who don't know, is someone who has completed a bachelor's degree and is currently working towards a master's or doctoral degree, also known as a PhD. It's very challenging work, and it involves a lot of effort and perseverance. Utah State University is very grateful for our graduate students who are vital contributors to the university's research and teaching missions. During our spring series, we'll be celebrating several graduate students along with their faculty mentors who are conducting fascinating studies. So tonight, we're very excited to welcome our featured speakers, graduate student researcher Abhay Katyal and his faculty mentor, Dr. Oscar Varela from USU's Department of Physics. Abhay is a fifth-year doctoral candidate in theoretical high-energy physics who works alongside Dr. Varela and previously with postdoctoral fellow Rita Brata Bhattacharya. Abhay completed his undergraduate studies at the University of Texas at Austin, where he earned bachelor's degrees in both physics and mathematics. Outside of physics, Abhay enjoys basketball and traveling internationally. He also works with the United Campus Workers for Utah to advocate for workers' rights in higher education. And if you're a regular to Science Unwrapped, you've probably seen him before. He's president of the physics group We All Matter in Physics and serves as the Department of Physics graduate student representative for USU. Dr. Oscar Varela, an associate professor in USU's Department of Physics, earned his doctoral degree from Valencia University in Spain. He works at the interface of theoretical particle physics and gravitation. Prior to joining USU, Oscar held postdoctoral appointments at Imperial College in London, the Max Planck Institute for Gravitational Physics in Germany, and at Harvard University in Boston. Oscar received a number of prestigious research awards, including a Humboldt Fellowship from Germany and a Marie Curie Fellowship from the European Union. He is active in organizing and advising regional, national, and international conferences, including the recent American Physical Society and Society of Physics students gatherings that were held here at USU. Oscar regularly serves as a journal reviewer and a grant panelist for the U.S. National Science Foundation. Beyond physics, he enjoys playing the piano and long-distance running. Please welcome Abhay Katyal and Dr. Oscar Varela for their talk about the duality of superconductors and black holes.
Thank you. Hello. Okay. Working. I'll turn the lights.
Oh, yes, please. Go ahead and dim them. Go lights. Yes.
Okay. Today we'll be talking about superconductors and black holes and how they're two sides of the same coin. So this over here is a superconductor. I'm not sure how many of you guys have heard of a conductor. It's anything that just carries electricity like a wire, and this is like an upgraded version of that. And it does this cool like floaty thingy, and we actually have a demo of this right outside. So you guys will be able to play around with it, but we'll come back. And this is a black hole. So these are really, really big objects in space. They like to suck everything in, and they're notorious for nothing being able to escape them. So today's talk is not actually about black holes or superconductors, but rather the connection between them and how these two things that seem completely different actually have the same physics.
Yes, because as Abhay just pointed out, a superconductor and a black hole at first sight have nothing to do with each other. The first is a material, is an object that you can actually hold in your hand. A black hole, on the other hand, is a massive object that lives up in the sky, completely different environments, completely different situations, yet we'll argue tonight that both things are deeply related in a way which doesn't meet the eye at first sight. And whenever that kind of situation arises in physics, we say there is a duality. A duality occurs when two apparently different situations, physical situations, are actually described secretly by the same physical principles. They govern secretly by the same physical laws. So the plan for tonight is to discuss that type of dualities in the context of black holes and superconductors, more generally in the context of quantum gravity, as we'll discuss, Abhay and I, later tonight. But for the moment, we're going to start easy, playing an analogy on dualities in a situation that I'm sure that, well, it will be familiar and it'll be outside of physics. Then we'll delve into the actual examples, some examples of dualities in physics. We'll go through various situations where these dualities occur in physics, and we'll describe why they actually matter and why they're important, why we care about them. It's just not we do this for fun, which we do as well, but there's a deeper reason why we actually care about these dualities. And one reason we actually care is because they give insights about open problems in physics, like, for example, quantum gravity, as we'll describe later today. But bear with us, because we'll be playing games tonight. So we're going to be playing a Physics Hall of Fame kind of game, and much more. So stay tuned, because there'll be prizes. And as Brinia pointed out in her introduction, please come collect your prize at the end of the presentation.
Yeah. If you answer any question throughout, whether you get it wrong, you can come up here afterwards and grab something.
Get it right or wrong, go and get your prize. Here we go with our first person of interest tonight. Can anybody tell me who this person is? I'm going to get a few guesses. I see a few hands up there. You with, what is that shirt? Buena Vista shirt? I get a Stephen Hawking here. Anybody, any other guesses? I get another Stephen Hawking? Stephen Hawking. And that is indeed...
Correct.
Stephen Hawking, indeed. Yes. Okay, so the reason why Abhay and I brought Stephen Hawking here, it's because he famously wrote a book in the late 1980s called A Brief History of Time, where he was famously advised not to include any equations in the book, which he kind of did, except for one, E equals mc squared, which unfortunately won't feature in our talk tonight. Sorry for the disappointment. But we nevertheless kind of followed his advice and not include any question. We didn't include any equations except for a few. Now the disclaimer is, don't be afraid of the equations. They're here for illustrative purposes only. They just regard them as pictures, okay? Like if they were decorative pictures. Having said this, let's move on into talking about our main topic tonight, dualities, with an analogy. Now, suppose you come to a new city, you're about to explore a city, and you're so excited that you just come to such an exciting place, and you just want to go and explore it. And well, you're full with excitement, which is a situation very similar to what Abhay and I experienced when we faced a new physics problem, and we're full with excitement to go and explore the details of it. Now, depending on whether you move around the city using the subway system, well, you'd use a map like this, where all you care about is that to go from point A to point B, well, you have to switch lines, say from the red line to the blue line at some other spots and things like that. But that's all you care about. You don't care what's happening at the surface level. You don't care about it. All you know is that this is your best description to move around the city in the subway system. However, you explore the city on the overground using overground transportation, then you'd probably use a map like this where it's not showing properly, but you have the roads and the streets and all marked on the map. And in this situation, you actually don't care what's going on under the surface in the subway system. So these two maps describe two complementary approaches to different descriptions of the same reality. And both approaches are complementary and they're useful for different situations, but they describe the same reality. We'll be discussing these kind of situations in a physics context, but this is a cartoon picture of what a duality is.
By the way, does anyone have any guesses? I don't know if I can use this. What city is this? Yeah? Anyone else? Yeah? You want to guess? Go ahead. Anyone in here? New York City? Okay. I'll take two guesses. Yeah, that's right. All right. So I would say let's start with the physics, but first let's play a game. We're going to play Cahoots. And the winner gets a prize.
The good news is everybody gets a prize.
Yeah. We all will get prizes. Let's start. I'll read the question out loud, and you'll have the choices on your phone. All right, first question. What are examples of dualities? And you guys get about 20 seconds? Oh, wow. That was quick. Nice. Do I go next? There we go. Okay. Nice. We got quite a few close ties. Next question. Why are dualities important? All right, let's see. A couple of people dropped out. What is electricity equivalent to? So what's another thing that works the same way as electricity? All right. Okay, we're halfway through. We got 3 more questions. Does gravity work the same on Earth and in space?
Say the right answer.
Yeah. It puts a check mark. Yeah. There we go. All right, nice. There we go. A conductor is something that carries electricity, like a wire. What's a superconductor? Good. I'm glad no one picked green, because the talk is about superconductors. Okay, last question. Einstein's theory of relativity teaches us which of these? Wow, that's impressive. Okay, let's look at the leaderboard. We have one special prize for first place, and everyone else who played or tried to play will have prizes for you afterwards. Marin. Who's Marin? You want to raise your hand? Good job.
Right after the talk.
Okay, awesome. Thank you for playing with us, guys. Let's see how I get out of this. And let's go back to the presentation. So thanks for playing that game with us. We left off at the city, and we did the cahoots. So now let's talk about some actual physics. Our first example of a duality is presented by this gentleman over here. Let's see if I can use this. Nah, I can't use this thing. Any guesses as to who this person is? Let's pick someone from there. Yes. Isaac Newton. Anyone else? Maybe back there? Isaac Newton. Yes. Okay, 3 out of 3. Yes, I'll take another one. Yes, very nice. This is Sir Isaac Newton, very nice. And the duality that he taught us about is how gravity works on Earth and in space. And earlier in the Kahoot, we talked about how they do work the same way. But here's my question to you guys. This is how gravity works in space. The planets circle around the sun in circles. But gravity on Earth, just like the apple, it's notorious for things falling straight down. Now, those two things don't look the same. In one case, we're moving in circles, and in the other, it's a straight line. So how come gravity does work the same in space and on Earth? So maybe think about that for a second. And the answer is that if you throw a ball, maybe sideways a little bit, you're sending it into a little bit of an orbit. So just like how satellites orbit the Earth, this is a mini orbit. And to see this a little better, if you throw this ball faster and faster and faster, eventually it'll get so fast that it can escape Earth's gravity. So really, that motion of up and down that we saw earlier is the same as the orbit. But I want to flip the script. So instead of on Earth, what about in space? This is the International Space Station. So if we're on a satellite moving in a circle, how is that the same as things falling straight down? Do you have an answer? Yeah? It's going around, and there's going to be a little bit of falling down. So you got half of it. Very nice. Okay, so maybe you guys have seen videos of astronauts like floating in space, and it looks like they have no gravity. This is where the free fall comes into place. This dog is not floating with no gravity. It actually has like 95% of the gravity on Earth. But what's happening is the dog is falling down. It's falling down towards Earth, but it's so fast that way that by the time it falls down, it actually misses the Earth. And then it falls down towards the Earth again, but it's going so fast that it misses the Earth. So this dog is actually headed straight down, just that you can't feel anything in a space shuttle. All right.
All right, and our second example for dualities is brought to us by this bearded gentleman. Any guesses on who this person is?
This is a tough one.
I see, this is a very hard one. The girl on the pink was that a hand? Was that a hand? Well, I can see a hand here. Who's Galileo?
Mm-hmm. Good guess, but
guess.
no.
That was a good guess. Max Planck.
That's also another good guess.
Very impressed.
Yes.
I can see a hand. Maxwell,
Whoa,
indeed.
okay.
This gentleman is Maxwell, James Maxwell.
That was impressive.
That was very impressive. All the guesses, though, were super impressive. You all get prizes. Anyways, what Maxwell taught us a number of years ago is that electricity and magnetism are, again, examples of dualities. They're two sides of the same coin. And it wasn't obvious back then, but, well, he, among other people, realized that an electric current is affected by a magnet close by, and likewise, a moving magnet can create a current as well. And this is an example of my disclaimer before. Don't be afraid of these equations. These are Maxwell's equations that actually describe what I just said in mathematical terms. Now, this E here stands for electricity. This B here stands for, guess what? Magnetism. The name is terrible, but we physicists are terrible at giving things names, like quarks and things like that. Anyway, But the nice thing about Maxwell's equations is that they stay the same if you swap E and B. You can do that mental exercise, swapping E and B, the equations stay the same, which means that electric phenomena and magnetic phenomena are actually, well, two sides of the same coin again.
All right. Any guesses as to who this person is? Let's look in the corner somewhere. Maybe I'll come back to you. Yes, in the very back. Wow. Good guess. Anyone else? One more guess?
I can see a hand up there.
Oh, yeah.
Who do you think? Who do you think this person is? Newton. We already had Newton, but yeah, that was a good guess.
Yes. Let's do final guess. Oh, Hilbert, okay. Mathematician, you're not too far off, but this is Erwin Schrödinger. Very nice. So he's often called the godfather of quantum mechanics, and he showed us the duality between particles and waves. So whenever you zoom into the universe, onto the smallest pieces, we usually look at those things, like atoms and protons and electrons, as tiny little balls. And waves seem to work completely differently. Waves, bobble up and down and they spread all around. So those two things are completely different. But what Schrödinger told us is that particles that seem like little balls actually move through space like waves. And here's a quick proof of that. So this is a demo where we have, let me play it right over here. So in this little simulation, we have water waves that are bobbing up and down. We're going to make them go through two slits. The bright spots, by the way, are the high points of this wave, and the dark are the low points. And if we pause here, you get this pattern where all the high points collect in the bright parts, and all the low points of the wave collect in these dark parts. This is how all waves behave. Now let's do the same thing, but with little tiny balls, electrons. All right. Oh, sorry. No. Okay. All right, I'll just show you. So we'll watch this video again. Right now, it looks like there should be two little slits that make two lines. But if you actually do this experiment with real electrons, you'll see that they make the exact same wave pattern as the waves with water. So electrons actually do move and behave like waves. And this is the famous Schrödinger equation. It looks scary, but we're showing this because this is the 100th anniversary of the equation. And yeah. Oh, sorry. Okay. So in this equation, this little symbol over here is for all of the matter, the electrons and the protons. But this equation is actually called the wave equation. So mathematically, we can see that something that is matter, like a little ball, actually works like a wave via the equation as well.
Okay, we already had a spoiler about our final character of the night. I'm going to take guesses, and let me give you a hint. This is not Newton. I can see a hand up there. I get an Einstein. You, yes. What did you say? Einstein. I get another Einstein. Einstein. How
Does
about
everyone
down
want to
here?
yell their guesses?
Albert Einstein. I'm going to take a couple more guesses. Up there? Einstein. Come on, guys. It's Einstein. It's Einstein. It's Einstein, indeed. Einstein brought to us a very interesting, very important duality. He described that gravity is dual, is a manifestation of the geometry of space and time. Now, as Abhay pointed out a while ago, Newton did describe how gravity on Earth and gravity in space work the same way, but Newton's theory left a key question aside, which is how is it that gravity propagates from one object to the orbiting object? And what Einstein realized is that, in fact, what happens is that gravity is a manifestation of the curvature of space and time, so that a big object warps the surrounding space, and a gravitating object just feels, a basin of attraction created on space and time itself. So this is a picture. How do we play this?
Let me start the little
This
simulation.
is a
By the
picture
way,
of what happens in
we
the
have a
3D
demo of this outside too.
On the 3D situation, which would look like this.
Yeah, so that demo that we usually see, it's only 2 directions, but we live in 3 space directions. This is what it actually looks like whenever you bend space. And in reality, you actually bend time as well. Sorry. There we go.
Anyway, Einstein said that gravity
Okay, there we go.
or geometry, which stands for G up here, you can take this for either geometry or gravity, again is affected by matter, T, well, really? Anyways, that's Einstein's equation. And, well, it just describes the interaction of gravity and geometry and matter.
Quick question. Did you have a question? No question? Okay,
Then we keep going.
let's keep going. All right, so why do dualities matter? Well, if you are doing research in any field, really, you're at the forefront of human knowledge. So we're exploring things that no one has solved before, and naturally, they end up being really, really big. There's a lot of things to keep track of, and they end up getting really difficult. So what dualities do is turn something that is really big and difficult and convert that into a much simpler problem. But here's the cool part. If you solve the simpler problem and get the answer will be the same as to the harder problem. So that's why dualities are so important. They turn very complicated problems into simple ones. Another reason why they're important is because of unification. So if we look at different parts of physics, an example is you guys are watching all of this with a projector and light, and you can think about charging your phone with electricity. So this is actually another duality that we didn't mention, but light and electricity are also 2 different sides of the same coin. And dualities help us kind of combine those ideas together and understand how they're all connected. Last reason, dualities help us tackle open problems. So an open problem is something that hasn't been solved. The problem that we're working on, quantum gravity, has been, I think, standing for 40, 50, well, okay, people have been trying for a lot longer than that, but many, many years. So dualities are probably the most essential tool for our subject to solve this open problem.
And in fact, one of the most important open problems that we face today is that of quantum gravity, and we expect dualities to play an important role in in elucidating what the answer to this question is. We've discussed Schrödinger and his theory of the quantum, of particles as waves, and we've discussed Einstein and his theory of gravity as geometry. Well, it turns out that the equations that we showed for Schrödinger and the equation that we showed for Einstein don't come together well, and they just don't go together. They just don't fit. So we need to come up with something which describes phenomena in physics that happens to have both quantum and gravitational effects, like, guess what? A black hole, for example. Now, that's an open question where we expect dualities to play an important role. And one candidate duality is the so-called gauge gravity duality, which is our specific topic. Abhay and I work on this, which is an interesting idea that describes the universe as a hologram. That's why it's called a holographic duality. This idea is interesting because it decouples the problem in the sense that gravity lives in a bulk, in a universe which is separate as a bulk of where the quantum theory lives on the outside of that bulk, in the low dimensional boundary of that bulk. And here's an analogy that Abhay can talk about.
All right, so this is a way to understand holography, which is that duality with holograms. So maybe you guys have seen like old TV shows, the question of how many gumballs there are in the machine. And it sounds like there's a lot. But my question, do you have a guess as to how many? I don't know. Probably. So my question to you is not how many gumballs are in there, but if I were to let you walk up to this machine and touch the outside, the glass of it, would your guess get any better? You think so? Okay. So no breaking of that. but maybe you're seeing it up close. But here's the cool part with holography. With holography, just by touching the outside and not being able to see anything inside, you'd be able to tell exactly, down to the number, how many gumballs there are inside. But not only that, you'd be able to tell exactly where each gumball is, and also the color of each gumball. So just by feeling the outside, it's kind of like you're using your fingers just on the outside boundary as little eyes to look inside. You're able to gather all of the information inside. And this is why it's called holography. On the inside of this gumball machine is where the gravity side lives. That's where black holes are. And on the outside, that's your hologram, is where the quantum sides of things live. So that would be things with electrons, like the superconductor. And those two things are related because they have the exact same information, but you only need to see one or the other. All right, so we're back to the title of the talk, superconductors and black holes. Let's see how they actually relate. So this is what a normal superconductor looks like. Those bigger silver balls are the center of atoms. And those little red balls are tiny electrons. So this is like electricity flowing. Each electron is one of those little red balls, and they're supposed to go that way, but every single time they bump into each other, they're actually losing a lot of energy. So whenever you're charging your phone or playing a game on your computer, you're losing a lot of energy. A lot of it's getting wasted. But a superconductor solves that problem. So first what we have to do is we have to cool things down and like negative 400 degrees. Cool. So this is really cold, and we actually have a superconductor outside, so you'll be able to see how this works. But what's happening here is that you're cooling stuff down to the point where the electrons don't have enough energy to jiggle around anymore. And then you get one electron that pulls the positive charge of the atoms close together. And because they're closer, they're able to pull an electron from behind it as well. So those two things kind of connect. And if I were to zoom out of this, a superconductor looks like this. You see, there's no hitting, there's no jiggling around at all. So there is no energy being wasted, and this is actually a 100% efficient conductor. And this is a cool application to it. So maybe you guys have seen bullet trains. This is one from Japan. And they're building an upgraded version of that that's set to complete in 2034 with superconductors. So they're going to have superconductors at the bottom of it. That way, just like the video we watched at the very, very beginning, the train is actually going to levitate over the track. It's not going to touch the ground at all, and that way there is no energy from the rubbing against the ground. So you'll have superconducting trains within 10 years.
All right, so just going back to our original theme of superconductors and black holes, and just to wrap it up, well, as Abhay just...
Do you have a question?
Did you have a quick question? Okay. All right, so we'll just a quick reminder that we'll have questions at the end, and we're about to finish in a couple minutes. Just to wrap it up, as Abhay just pointed out, superconductors is something that we have under much better control than the physics of black holes, and yet that turns out to be striking parallelisms that hint towards the existence of a duality that we can exploit to learn more about black holes. Let me just briefly go through some of these parallelisms. Suppose that we have this piece of material before it undergoes the superconducting transition. It's just a regular conductor, as Abhay just showed, and it conducts losing energy. Now, it turns out that we also know that surrounding black holes, that turns out to be matter as well, that can fall into the black hole, thereby losing energy as well, just like currents do in a usual conductor, in a usual material. Now, on the material side of things, you can lower your temperature. And it turns out, remember our first slide where we had Stephen Hawking telling us about his equations and whatnot? Well, one of the things that we learned from Stephen is that black holes turn out to have temperature as well. Believe it or not, black holes do have temperature. Now, suppose I had a dial or something close to my black hole that I was able to turn it down and lower its temperature like I can in my material. Well, as Abhay pointed out as well, at some point, at some critical temperature, a superconducting condensate forms in the material. And it turns out that our equations show that the matter surrounding a black hole undergoes a similar transition, and there's some condensation as well. Now, we know from the superconducting side of things that under that phase transition, the material turns out to undergo a superconducting, turns out to reach a superconducting phase where electricity is conducted with no resistance at all, with perfect efficiency without losing energy at all. Our equations do show as well that similar things happened on the black hole side of things, where that condensate orbits the black hole without losing any energy, thereby paralleling the effect of the superconductor. Now, this is a little bit of a toy model, admittedly, but what it does teach us is that there's a lot to learn from unrelated physics to quantum gravity that can teach us lots about things like black holes, for example. And that's very exciting.
All right, so apologies for throwing so much information at you guys. I know that was packed. So let's do a quick little summary. We first talked about dualities and how they relate things that seem really different, but they're actually the same. And then we talked about how they are a powerful tool. I would argue the most powerful tool for us theoretical physicists in helping us solve our problems. And specifically, they help us figure out how the quantum world, the world of the really tiny and small, and the gravity world with big stars and galaxies and black holes, how they fit together in a theory of quantum gravity. And they'll also let us take a little peek inside of black holes with our holographic principle. And for you little kids, we have another duality. Your 6-7 duality. 6-7, yes.
And don't forget about your prizes. This is the
All
end
right.
of it.
Yeah, thank you guys for listening. If you answered any questions, or if you tried to answer questions, feel free to come down and grab some prizes.
Feel free to come down to get your prizes. Over to you.
Thank you, speakers, very much. Hands up, who's got questions for our speakers tonight?
Okay. Yes. We're supposed to alternate?
So, how is it possible that black holes, delete information?
Ooh, the information paradox. So that's a really good question. Let's see how I can explain it. Whenever something goes inside of a black hole, there's no way to get it out because black hole has such strong gravity that nothing escapes, and the famous saying is that light can't even escape. So if you think about how our world works, I am only able to see things because there's light. The light bounces off of objects and goes into my eyes. But if I'm near a black hole and the light goes inside the black hole without coming out, then I can never see anything inside. So that way I can never gather or get any of the information out of there. And in that sense, I mean, there's a lot more to the picture, but information gets destroyed, sort of. Mm-hmm. Ooh, okay. And I forgot to repeat the question. So the first question was, what happens with information in black holes, or how is it destroyed? And the follow-up with the singularity. The singularity is famously the middle of a black hole. And the truth is we don't actually know. So those are all just guesses, and we use math to try to justify our guesses. But it could be a single point. It could be a circle. With spinning black holes, we actually do think it's a circle. It's a little bit of a ring. It could be a moment in time, whatever that means. So the only sure way to tell is to actually go in there and look, but then you're not coming back out. So yeah. Really good question. Yes?
In the image that you had of the superconductor on the screen, there were 2 electrons in pairs. Why are they in pairs?
Yeah, that's a good question. We kind of flew through that one. So I have a diagram that'll help explain. So that's a hidden slide, but you get to see it, or maybe not. There we go. Okay, so this is a hidden slide. What happens is that these electrons are so slow because things are so cold that everything kind of stops moving. And an electron has a negative charge, and the center of atoms have positive charges. So the first one is going to pull these positive charges together, kind of like squish them in. And because you're getting these positive charges closer together than usual, these guys pull the guy behind it as well. So you kind of get them attached in pairs, and they're called Cooper pairs. But very, very good question. Yes, do you want to pick? Or? Yeah, okay, they're passing around the mic. Do you want to?
Why would they be in pairs instead of like a whole chain? Like wouldn't it be like a, why just two?
What's the question again?
Why would the electron pairs be only pairs instead of a whole like chain of electrons stuck together?
Oh, well, this is an observation. That's what happens, and what we know is that the condensates turn out to form pairs. That's an experimental fact. And the curious thing is that a similar thing happened in the matter surrounding the black hole, which is not supposed to follow the same pattern, and nevertheless it does. Now, having said this, superconducting not only occurs with Cooper pairs. There's other types of superconductivity that are not created by Cooper pairs, and those are the so-called high temperature superconductors. The mechanism is altogether different. But as far as the BCS theory, the Cooper pair formation is concerned, well, that's just an experimental fact.
Yes.
Do you want to take this one?
How to lose zero energy if it's not absolute zero? Because if something's not absolute zero, it could still lose energy.
Yeah, really good question. So absolute zero is where everything stops moving, like altogether. But we don't have to have everything stop moving altogether. All we have to do is make things not bump into each other. So if you think about maybe like you're on your way to class and you trip on a stair and fall down. You're hitting the ground, and that makes the energy waste. If you think about a car crash, like the trunk, the front of a car crumples up, that's all the energy from the crash. So only when two things hit each other do they waste energy. And they can still move around, but if they don't hit each other or they're not hitting unnecessarily, then you're not wasting energy. They're just going straight from the starting point to the destination, which is your computer or whatever you need the electricity for. Does that help? Or do you have a follow-up question?
One more thing. So if you could tell what's inside of a black hole, like how could you tell what's inside of a black hole from the holography?
So how can you tell what's inside of a black hole if you can never go in? Yeah, I mean, that's why I said earlier that we actually don't know what's inside of a black hole. But what we do know is that the math we used to figure out what things or how things behave around a black hole should also work inside of a black hole. So everything works perfect. Like we know how black holes are formed. We know how black holes eat up other things like stars. And all of that we can use math to figure out. So we just use the same sort of math to try to see what would happen inside. So we have some idea, and it's a guess. And some people have other guesses, so there's a lot of disagreement in some circles where people don't actually agree what might be inside. And we might not know for a while, but maybe we will. I don't know.
And if I may follow up
Follow
on that question, that's a very interesting question. In fact, that's actually related to what Abhay do and I do for research. We don't know what happens inside the black hole, but we do know that there's some structure to it. And one of the striking things that we know about black holes is that they're holographic. That's why we call this principle the holographic principle. Turns out that most of the information that that the black hole stores is not contained in the volume surrounding the so-called event horizon. It's in the area surrounding it, just at the horizon. That's why it's called holographic, because the information is stored in a surface rather than on a volume. And well, that's pretty striking. But one of the things that the holographic correspondence does, the holographic duality does, is to help us understand why that happens, why that information is stored at the horizon rather than inside the black hole.
Yeah,
I can see a couple hands.
Okay, we'll go over here, and we'll come around to everyone. Don't worry.
What does a black hole suck in?
That is a very interesting question. The question is, why does a black hole suck in?
Oh.
That is, you want to have a go at that?
Okay, so the reason things go inside of a black hole is because we can look through a telescope and we see that's how they are. So we've seen that happen plenty of times to think that that always happens, but the math helps us show that, and there are possibilities where it doesn't do that. So maybe you've heard of something called a wormhole. It's like a little portal from one place to the other, and in that case, gravity actually works the opposite way. Instead of pulling in, it'll push things out. So one end of it will pull you in, and the other end will push you out somewhere else in the universe, and you can go from one place to the other, and that is a real thing. We don't know how to make one. We probably can't make one in the near future, but the math does work out. So gravity can behave the opposite way, but the only way we've ever seen it behave is by pulling things in. That's an awesome question, though. Yes. Yeah.
So I was like really intrigued by this topic, and so like I don't know, a couple months ago or something, I spent like a month researching, and I'm like and I zeroed in on the fact that you know what exotic matter, you know?
We're talking about exotic matter?
Yeah, exotic matter.
Oh, dark matter. Oh, dark matter, sorry.
No. Like, sorry, I use it as a phrase. You know, like like matter with a how do you put it?
Dark matter?
No, not dark matter. You know, like, you know how a rock and you know how like the Earth pulls in like an exotic Earth.
Like we're talking about gravity here on Earth?
Yeah, you know, like how like I would say, like an exotic Earth would be like one that rather than pulling in, use that same energy for pushing out.
The dark energy.
Are we talking about? Well, let me. Okay, so I suppose.
Yeah.
Oh. Right. Okay, so I don't have a clear picture what you actually refer to, but maybe what we do know is that there's two types of attractions out there, attractive and repulsive. And what we do know is that some interactions show the two types of behaviors depending on the charges that objects have, and some others are effectively, attractive. And gravity is one of those. That's probably one way to put it. Having said this, though, we do know that the matter that we observe in the universe is just a small fraction of what there actually is, and the highest portion of what's out there in the universe, we actually don't have the slightest idea of what it is, and in some sense, that does behave as a repulsive gravity force. This so-called cosmological constant. I don't know whether that's probably one of the things that you're referring to. Dark energy. Those are effects that behave as if gravity was repulsive, and that creates the universe, for example, to expand.
So like I found out, like, after connecting the bases, I'm like, if you throw some dark energy into a black hole, it would effectively turn it into a wormhole.
It would, yeah. Well, I don't have a concrete answer to that, but yeah, there's a lot of stuff that can happen in a black hole, and everything that throws into the black hole stays in the black hole. That was a great question, Umar. Do you want to follow up on that?
Sure. Yeah. So just really quickly, while the next question is being asked, there's two flavors of electric charge, positive and negative. We don't have that for mass, for matter. And it's kind of weird. People think that maybe there should be something. There are weird things. There's antimatter, but antimatter does not push away. It also pulls in. So it's a little weird. And like Dr. Varela mentioned, there's things called dark matter, which also pulls in, and dark energy. We don't think it's like a different anti-gravity thing, but it behaves as if it was anti-gravity. But short answer is we don't know a lot about our universe. We're still trying to figure it out.
We'll
Yes.
probably do 2 more questions for sake of time. One's right here.
So how concrete is the proof that we have that even light does not leave black holes?
Oh yeah, it's extremely concrete. And that's why black holes look black. Yes, sorry, thank you. So what proof do we have that light does not leave black holes? It's a very legitimate question. And the answer that we have is actually in the image that I showed earlier. The reason a black hole looks black is because there is no light coming from that point. So you're not actually seeing the black hole, you're just seeing the absence of light. There is no light coming from the center, but you can see light that's around a black hole that's not quite in yet, being able to escape. And that's the ring of light around it. So we're extremely confident that once the light goes past the event horizon into the black hole, it will not leave. Do you want to follow up on that or any other questions?
I guess we're given one more question.
Yes, who wants to take the last question? You? And we'll be outside, by the way, with the table. So if you want to ask us more questions, then you can.
Is there a limit to how much a black hole can like hold around it?
Ooh. No. Black holes can get really big, and we actually see these things called supermassive black holes. A lot of them are at the center of galaxies, and they actually hold our Milky Way galaxy together. Otherwise, all the stars would sort of fly outwards. So these black holes can get really, really big, but usually they don't keep stuff just around it. Usually they'll slowly pull it in and eat it up. And when they eat stuff up, they get bigger. So there's really no limit that we know of how big they can get. All right. I think we're done, or should we take more? I don't know.
That's up to Brian. She's the boss.
Yeah. Okay. We'll keep going.
Can
Yes.
gravity exist without matter?
Gravity can exist without matter. Gravity exists with energy. And maybe you've been told that light doesn't have mass. So if you were to somehow take a little particle of light and put it on a scale, it would read completely 0. But light actually has gravity. And that's the reason it gets sucked into a black hole. It has gravity from the energy it has. And we know it has energy because whenever you step outside in the sun, you see that the sunlight actually warms you up. It's giving you energy. So a lot of people say mass is what creates gravity, but it's secretly energy. And mass is a form of energy with the whole E equals mc squared. Is that a good question? Yeah. Yes.
I guess there might be 2 questions, but my first question is, earlier you showed up a picture of what I presume to be Cooper pairs in a superconductor. My question regarding that was, why exactly do Cooper pairs form and not other...
Like Cooper triplets?
Yeah, a Cooper triplet. Does that have to do with like spins or like the amount of states?
That's a follow-up on another question we had earlier on. So that's an experimental fact, but the equations do show, based on things like spin couplings and things like that, that this the pairs is a natural condensate to form. But other than that, what I understand is that the theory is mostly experimental, and the fact that Cooper pairs are formed is just an experimental observation, which is backed by the BCS theory.
Interesting. And then,
and I want to add something on really quickly to that. So Cooper pairs, they're pairs, so two things. But really, superconductors can still work as long as it's an even number of them. We just don't want it to be odd, and it does have to do with the spin of the electron. So that's right.
okay.
But whenever you have 4 of them, it's really hard to keep them all together. It's really easy to break like the bond between them. So usually the pair, the two things attached, are the only ones that are stable and left. But really, we just want an even number of them stacked on top of each other.
I see, to complete the
Yeah, exactly. Yeah, you need 1 up, 1 down, and the total spin number would be an integer instead of a half integer. So instead of 1/2, it would be 1.
like a boson.
Exactly. It's literally just fermion becomes boson. That's perfect.
Okay, that makes a lot more sense. But like you said, it's like this is an observed thing, like a.
Yeah, this is an observed thing.
It's empirically, I suppose. This is wrong. Anyway.
So like black holes hold galaxies together, right?
What's that again?
Black holes hold galaxies together, right?
Black holes, these supermassive black holes are the center of galaxies now, and the galaxy sort of gravitates around the black hole, if you will.
But what holds black holes together?
Oh, that's what we do for a living. We don't know, so we're trying to understand that. We're trying to figure that out.
I mean, like, is it the singularity, or is it like the matter that hasn't become part of the singularity that actually?
Okay, so here's the S word. The singularity is just a word to say where things just crack down. It's just a name for things that we don't understand. The reason why there's a singularity, it's because it's actually it's because our theories just break down, and our theories just don't tell us what happens at the singularity, but we know that there should be something going on, and that's the purpose of quantum gravity, to understand what happens at the singularity. And there's 2 types of singularities that we know of, at least. One happens inside a black hole, the other one happened at the very beginning of everything, which is something that we don't understand either. But both are relatively related.
And should we be, you know how the Big Bang happens from a singularity?
That's the one I was referring to, yes.
Yeah, should we be scared that, like, say, this, like, like a Sagittarius A star, you know, like our galaxy's black hole, should we be scared that it will spawn a new universe?
I only got that. Should we be scared of something? I guess we should, but I'm not exactly sure of what. Can you repeat your question again?
Something about spawning a new universe.
I was talking about multiverses or something like that. Yeah, well, that's an interesting question. I don't have a definite answer to that. Now, what might happen is that there's a big crunch further down the line, but we won't be here to see it, so never mind.
It's possible. There's white holes that are theorized. We don't know if they exist, but they could make a new universe out of a black hole. It's probably not happening to us. Yes?
How do you make superconductors so cold?
Ooh, that's an awesome question. And you're actually going to get to find out outside, because we have a superconductor out there. So we use something called liquid nitrogen. Liquid nitrogen's super cold, like negative 160 degrees. So it's not quite as cold as the temperature I put up there, which is why it only works as a superconductor for a little bit. And eventually it falls down. But yeah, we have to figure out weird, creative ways to cool things down that cold.
Okay, thank you.
Yeah, very good question.
Let's now thank our speakers one final time, and thank you all as an audience for being here tonight. But we'll end our session.